Hello, and welcome to Tomversations, a regular conversation about a variety of technical topics, starring me, your host, Tom Hollingsworth, the networking nerd. Today, I'd like to talk about computers. Well, sort of. If you recall in my previous episode, episode 9, we talked about post-quantum encryption. And in that episode, which you can find linked in the iCard that just appeared above my head, I said that quantum computers would take a little bit more explanation than was warranted in the scope of that video. Well, I decided that this is the video where we're going to talk about it. So we're going to talk about quantum computing. But in order to understand quantum computing, I have to give you a really quick lesson in quantum physics. So if you're watching this at home, make sure you put your nerdy glasses on because this might get deep pretty quickly. In essence, quantum mechanics is the idea that traditional physical models don't accurately explain the way that matter and energy interact in our universe. In short, particles act like both packets and waves. They have qualities of both, and they act at a very small, discrete level. And when that happens, weird things can occur. Two of the weirdest things that we have determined in quantum physics are very applicable to quantum computers. The first is something called the uncertainty principle, which was coined by a scientist named Werner Heisenberg. Essentially, Werner said that if you try to measure something, say an electron in a classical atom, you can know where it is or you can know how fast it's going, but you can't know both because as soon as you measure one of those things, you change the other. Now, if you look at the model of the electron that I have up next to my head right now, you see that when we simplify the drawing, we draw these little particles flying around the nucleus of an atom, kind of in an orbit. And that orbit looks like a traditional planetary orbit. But in fact, it's not. It looks more like a cloud that surrounds the entire atom. We don't know where that electron is, and we don't know how fast it's going, but we're relatively certain that it's there, because if it's not, then all of our models are wrong. So there is an observer effect in quantum mechanics. As soon as we measure something, we change it. Put a pin in that because we're going to come back to it very shortly. The other idea is something called superposition. And in order to illustrate superposition, I'm going to reference the most famous cat in scientific history. And it comes from a man named Schrodinger. Schrodinger's cat is an experiment where the scientist said, I'm going to put a cat in a box with a poison that's activated by radioactive decay. When I close the box, any attempt to open the box will activate the radioactive isotope and the poison, killing the cat. However, at some point in the future, since all atoms decay, the poison will be activated. So is the cat alive or dead? Well, if we open the box, we will know for sure. It will have to be in one state or the other, alive or dead. However, while the box is closed, the cat is simultaneously in both states. It is both alive and dead because it has to be one or the other, and until we observe it, we don't know which one it is. So many cat jokes have been made in physics because of Schrodinger, but the idea that something can exist in multiple states at once until it's observed is very important to quantum mechanics, and we will come back to that in just a minute. The other things you need to know about quantum mechanics are entanglement, where we cause two particles to take on the same state through the use of energy bombardment. So if a particle is spinning one direction, we can entice another particle to spin in the exact same direction, in the exact same frequency. And by observing one particle, we can infer what the other one is doing without looking at it and causing it to do things that it's not supposed to do. Which leads us to the other principle that we need to talk about, which is quantum decoherence, which is essentially once we've looked at something, we cause it to blink out of existence. When we add energy to a quantum system, it destabilizes the system or causes it to decohere. That can happen in a fraction of a second. So we better hope that whatever data we needed to get from the system is captured before it explodes into nothingness. All right, sufficiently nerdy for you? Are you an expert on quantum physics? Good. Let's apply the lessons that we just learned to building a computer out of it. The idea behind a quantum computer has been theoretical all the way back since the late 80s and early 90s. However, it didn't really start taking off until Peter Shor theorized that quantum computers could be extremely good at factoring very large numbers very quickly. And you will probably recall from episode 9 that I talked about Peter Shor kickstarting all of the research into quantum computers. In order to understand how a quantum computer works, you have to understand something called a qubit. And no, I'm not talking about what we use to measure the size of the arc. I'm talking about a QUBIT, a quantum bit. Traditional computers use bits to store data. However, a traditional classic computer only has two states. It's on or it's off. It's charged or uncharged. If you're a fan of binary math, you probably know that these are represented by ones and zeros. A 1 is on, a 0 is off. And that bit can only be in two states. A qubit, on the other hand, looks more like a sphere. And there's a high probability in that sphere somewhere that this bit is going to be this value. However, that value can be a lot of things. It could be 30% on and 70% off. It could be 57% on and 43% off. And the variable nature of what a qubit's data contains is one of the reasons why it can be well suited to solve problems that classical computers have a very difficult time with. All right, so let's go back to this idea of superposition right now. So you'll recall that I used Schrodinger's cat as an example of a superposition, but I actually have a great example of this that comes courtesy of some of the brilliant minds at IBM. I want you to think about a US quarter. If you are from another country, pick one of the coins that represents your monetary system. Flip that coin in the air and let it land, and then observe the state of the quarter. What can it be? Well, it can be heads or tails, or if you were extremely lucky, it might land on its edge. But for the sake of argument, let's just say that right now, the only two states of that quarter can be heads or tails, because it matches the classical computer bit of on or off, right? So that's the state of the quarter when it lands and we observe it. What's the state of the quarter when it's in the air, when it's flipping around? Is it heads? Is it tails? Is it both? It's both. While a quarter is flipping in the air, it has quantum superposition. It is all possible states at once until it is observed. Cool, huh? A qubit is all possible states until we observe it to collect data from it. Now, if you own a pair of noise-canceling headphones, you are using an idea of quantum mechanics, interference. Noise-canceling headphones listen to the ambient noise around you and create a waveform that is exactly the opposite of the noise that wants to be filtered. And then it plays that waveform back against the ambient noise that it's collecting and cancels out the noise. Likewise, if you can collect the data about the waveform that you want to study and play a sympathetic waveform against it, you can amplify the noise that you want to pick up, which is also how noise transparency works on noise-canceling headphones. We can do the same thing to a qubit. When we put qubits into a quantum computer and we observe the state that they are in, the wrong answers cancel each other out. They fall out of the bottom of the qubit. And what eventually comes out of the other side should be the right answer, provided we can put enough power into it and we can observe the results. Pretty cool, right? Why do we have to entangle those qubits? Remember I talked about quantum entanglement, wherever you can entice a bit to take on a certain characteristic and you can observe the partner bit to infer what the other bit is doing. Remember how I told you that Heisenberg said that as soon as we look at something, we change it? The observer effect is very real in quantum computing. So we have to entangle bits for error correction. And I'll talk about that in just a minute. But remember that qubits can be entangled just like any other elementary particle. You probably have heard the term quantum supremacy being thrown around. This is not machine AI taking over the world. Quantum supremacy refers to the fact that there are certain mathematical operations, or certain problems that a classical computer will never be able to solve in a reasonable amount of time. A simple idea behind this is trying to factor an encryption key that's 128 bits long. The reason why the RSA algorithm works is because taking two prime numbers and multiplying them together to produce a product to sign a private key with 128 bits would take a classical computer trillions of years to work through the 340 undecillion possible values that could be created. So we're relatively certain that a classical computer will never be able to crack quantum encryption. However, with quantum supremacy, what we're saying is that a quantum computer can find that value much, much quicker. And much, much quicker could still take hundreds of years, depending on the precision of the quantum computer. But we'll get to that in just a few minutes when we talk about the challenges of quantum computing. All right, so if quantum computers are so great and quantum computers are amazing at doing things, why haven't they completely supplanted traditional computers yet? Well, just like the problem that we ran into back in the late 19th and early 20th centuries when people were trying to justify why automobiles were a much better solution and customers all they wanted was a slightly faster horse that ate less hay, traditional computers are still much, much faster at certain operations, especially when they don't require very complex things. Here's another problem. Quantum bits or qubits require very, very cold conditions to operate effectively. Qubits today are made out of superconducting material. And in order to make that superconductor work the way that it's supposed to, it must be cooled to within a few degrees of 0 Kelvin. And for those scientists out there, you'll know that 0 Kelvin is absolute zero, the temperature at which no energy can be transferred through a material anymore. So by cooling this thing to within a few millionths of a degree of Kelvin, we can make it superconducting, but we also waste a whole lot of energy getting it that cold. Remember I talked about entangling qubits to create situations where we can observe one without impacting the other one? We're doing that for error correction. So here's one of the standard problems we run into. If we have a group of, say, 3 bits of anything, and one of those bits goes away, we've lost a third of our data. In traditional systems, what we do is we make a copy of that bit. We make a backup, or we create some kind of a parity system. If you've ever worked on a storage array that uses RAID, a redundant array of independent disks, you know that RAID is essentially a mechanism for us making sure that everything is consistent across the drives that we're storing them on. That's great. You can make a copy of something when it's deterministic. It's a 1 or a 0. What happens when we're not exactly sure what state that bit is in? If we make a copy of it, we've changed it because we've observed it. Hence quantum entanglement. We entice a bit to take on the properties of another bit, and then when we observe that bit, we know what the bit we originally wanted to look at should have been. That also means that we have to have 1 qubit for every bit we want to entangle. And quantum entanglement is not the easiest thing to do in the world anyway. The other problem that we have is relating to compute power. So if you're someone who has an Intel or AMD PC and you have been playing the game of trying to get as many transistors packed onto that circuit as possible, you know that traditional transistors create a significant amount of heat that is wasted away. Quantum computers don't do that. In order to increase their compute power, they don't add transistors, they add qubits. The more qubits you have, the more computational power you're capable of pulling off. However, remember I told you that qubits sometimes do weird things? Guess what happens when you get a whole bunch of them together? They start creating more and more noise. And that noise has to be error corrected. So you either have to dedicate a certain number of qubits in the computer to correcting that noise, or you have to learn to filter it out with error correction algorithms. You probably saw a story from, I believe it was last year, 2019, where Google was able to say that they had successfully achieved quantum supremacy with a 53 qubit quantum computer. That made all the headlines because, well, now the AI overlords are coming to get us. Fun fact about Google's 53 qubit quantum computer, 99% of the data that was produced in that quantum supremacy trial was noise. 1% of the data was usable to prove quantum supremacy on a small scale. And as I talked about in my post-quantum computing video, Until we can provide sufficient error correction for a quantum computer, it's like having a very fast sports car with no steering wheel. We can go really fast, we just don't know which direction we're headed in. The other problem is once you get that many qubits together, you're going to have massive decoherence issues, because as soon as you observe one of those qubits, it's going to have an impact on the rest of the system whenever you have it in some kind of a stasis. This is actually one of the problems with decoherence. In a perfect scenario, all of the qubits will contain their state forever. But there's no such thing as a perfect scenario in quantum mechanics, because as soon as you introduce outside data from observations or energy, you cause the system to start decohering. So you could spend hours getting the system into the proper state to observe and have less than a second to grab the data from it. Doesn't sound much different than something like the Large Hadron Collider at CERN. You can spend hours or weeks or days trying to set up your experiment and have all of 3 seconds to collect all of the data. All right, so quantum computers are hard, but they give us a lot of potential capabilities. What are those? Well, the first one we talked about in episode 9 was the idea behind factoring large numbers quickly, and that was Peter Shor's algorithm. Other things that can be done with it are quantum search, where instead of writing a simple double sort, we can apply quantum mechanics to quickly sift information to the top of the heap. And that uses Webster's algorithm, which will be linked in the show notes. What else is quantum computing really good for? Well, we have to go all the way back to the original reason that massive supercomputers were built in the first place, and that was weather prediction. Anyone who's ever tried to predict the weather or natural phenomenon know that classical computers tend to barf on the large amounts of data that they're required to do, and the fact that no 2 runs of the simulation produce the exact same outputs. Anyone who lives in Hurricane or Tornado Alley knows that forecasts can vary greatly on an hourly basis because the models can change significantly. Quantum computers can see a variety of different states at once and bubble the correct solution to the top. So quantum computers are heavily hoped to be able to model natural phenomenon with a much more accurate algorithm. And lastly, the excitement behind quantum computers is finding problems we had to solve. So think about all of the things that we have developed in the last, say 60 or 70 years since we have developed computers. We have been able to solve massive problems. We have been able to create things like AI and ML, which allow us to predict certain behaviors or find data buried in the noise. And we wouldn't have been able to find that if we didn't have some kind of a computer. But we had to find the computer in order to find that problem. Quantum computers are hiding problems we didn't know we needed to solve. We just have to be able to complete quantum computers big enough to have the data to show us the problem that allow us to go solve it. Thank you for joining us today. I know this was a pretty heavy episode. You might have to watch it again, and you're definitely going to want to check out the links in the show notes, because there is a lot of great data that's hiding out there that can teach you how quantum computers work. There are also free quantum computers available online for you to use and to test out and to see if you have what it takes to make a quantum leap in computing technology. There are more great episodes of Tomversations on our website at gestaltit.com. There are also other great shows that you're going to want to check out, such as our Checksum series or our on-premise IT roundtable, and more great technology articles. You don't want to miss any of those. Stay tuned for more great technology topics on Tomversations. And if you want to leave a comment or perhaps a topic that you want to cover in the future, please feel free to do so. And I look forward to having another Tomversation with you again soon.